Thank you, Ivona, for the invitation and the nice introduction. So, hello, everyone. I'm going to talk about today our new project starting from beginning of this year called GreEnergy. So this is about energy harvesting using 2D materials. And first, I would like to quickly introduce AMO. So I guess most of you don't know about AMO. So we are located at very west of Germany, so very close to Netherlands and Belgium. So it's a city called Aachen. So our managing director is Max Lemmer and Michael Hornung. And Max Lemmer also holds a chair in the University of RWTH in Aachen. And we are a non-profit company. We have a 400 square meter clean room. So as you can see here, so this level, the first level, is actually our clean room. And we are quite relying on funded projects. So because we are non-profit, but of course we also offer different services in fabrication. So our key technology traditionally it's based on silicon, and we also have different nanofabrication, especially in lithography, like e-beam or imprint lithography or interference lithography. We are also interested in new materials this year, especially for example, the graphene and other 2D materials. That's also what I'm going to talk about today, and also perovskites. Actually, it's a hot materials in this years. And the main application is electronics, photonics, and integrated sensors. As Ivona already mentioned, we are also part of this Aachen Graphene and 2D Materials Center. If you're interested, you can have a look here to the website. I think you will find very interesting there. And I'm not sure if you can see my title, because here it's actually blocked by this Zoom bar. Yeah, but nevertheless. Here, I would like to talk about what we are mainly doing in my group, Graphene Electronics group. So we are also doing TMDCs. So our main focus is actually on high frequency electronics. As you know, graphene has a very high mobility, so that's why it's so suitable for high frequency applications, and also flexible electronics because of its high mechanical strength. And also it can be used for different sensors. For example, here we have graphene-based membrane, as you can see here. And also we would like to make this kind of process compatible with large scale. So we try to scale our process as well. So I will start with the device, which is we call it, sorry, it's a little bit strange here. Metal insulated graphene diode. So this is what I'm going to mainly talk about today. So we are actually inspired by this work in 2016, and we improved the structure there, and then we get this paper published in 2017. So it's about this metal layer, titanium, and titanium oxide as the insulator, and on top of it we have graphene. So the nickel is actually the contact electrode for graphene. So if you have a look to the band diagram, you can see that so we work with some groups working on simulation. So in the end, we observe that there is a bias-induced barrier lowering. So that makes this kind of diode works really nicely, so that in the end, if you measure this diode, you get a typical diode behavior. And also we did some benchmarking with MIM diodes. I believe that the MIM technology is also improving in the meantime, but I think this table was quite old, so we should definitely update that. So as you can see here, our graphene-based diode has very high on current, and also it has very high asymmetry, very high nonlinearity, and also responsivity. So I think asymmetry is not as high as MIM diodes, but others they are higher than MIM diodes. So that's why we think this kind of diodes is very promising, and we are working on improving that. So we also shown that this kind of diodes can be used for power detection. So here we have shown to induce an AC input to the one side of the diode, and we measure the output. As you can see this plot here, so the axis is the input power and y is output voltage, DC voltage. As you can see, this kind of diode can work up to almost 50 gigahertz with a sensitivity of 1.1 volt per watt. And we can also actually fabricate integrate circuit based on this diode. So we can integrate resistors and capacitors and inductors, and all in one process. And we have fabricated all different devices in collaboration with RWTH Aachen University. And recently we have a review paper on this with advanced materials. It's under review. And as I said, we're trying to also to improve this kind of diodes by doing some device engineering. So this is an example here. We try to make this diode to one-dimensional variation, namely that we try to make this junction here at the edge of the graphene. So here the red part is the 2D sheet of graphene. So, and then we form a barrier layer at the sidewall of this stack, and then we make an electrode here. Then as you can see, this diode junction is actually a one-dimensional line. So that's why we call it 1D MIG diode, metal insulated graphene diode. So what is the advantage of such a diode? So if we compare to the 2D version, so that's what I have talked before. So as you can see here, since this barrier layer is actually directly contacted with the edge of the graphene, so which makes the contact resistance or the junction resistance much smaller, so that it has a lower resistance. And of course, we can also tune the length of this graphene so that in the end, we can also reduce the series resistance drastically. And also, it has very low capacitance. I think this is really the main point for this 1D variation, because this area of this junction is really small, because the thickness of the graphene is only 0.3 nanometer. So the capacitance here is proportional to the area of the sidewall. So that's why if we combine these two, then we can conclude that we will get very high cutoff frequency, so which is dominated by the RC. So we did a calculation based on such a structure, and the theoretical value of the cutoff frequency is 2.4 terahertz actually. And we also have a review paper on advanced electron materials about these two different diodes. And we also, as I said, we are interested also in flexible electronics. So we try to integrate this kind of diode also on flexible substrate. As you can see in the middle of this device, we have such a diode. So this 1D variation, and then it's connected to such a bow tie antenna. So we collaborated with the University of Chalmers. So we did the measurement there. So we shine a terahertz signal here, and then in the end, to directly in free space to our sample, and then we measure the DC output from this diode here through this two conduction line. And we were able to measure up to 170 gigahertz, which was limited by the measurement setup there. And this paper was published this year in ACS Applied Electronic Materials. And yeah, so then we were thinking, if we go for even higher frequency, namely the optical frequency, then it leads us to this GreEnergy project. So here in this project, we work with different partners, and the target is to realize optical rectification. So in the end, sorry, yes, just a little bit, yeah. Sorry for this. So this is our system overview. So in the end, we would like to first start with this rectifier. So this will be based on graphene. So our current plan is to use geometrical diodes, or the so-called plastical diodes, for rectification. And this kind of diode is also connected to nano antenna, which is responsive to optical frequency. And so in the end here, we will get a rectifier, which can rectify sunlight, hopefully. And the next step is we try to connect this output to our energy storage unit, which is here. So this is based on this. So this is a super capacitor here, which is developed by Chalmers University. And then between these two components, there will be some power management unit. And then this will be evaluated actually by IHP in Germany. So this is Leibniz Institute. And yeah, I forgot to mention that here, both Aalto and Aalto University in Finland are working on this rectifier, since the challenge is so much here. And also we have some support from the simulation side, University Udine and University della Marche in Italy, both universities are in Italy. And also we have Nago Photonics Ltd from Israel to do the system integration. And also we have a partner for management and dissemination from Switzerland. So this is overview of this project. It starts from the beginning of this year, and I hope we are now actually still working on realizing our first diode. Yeah, so it's just started. Of course, we already had a lot of discussion with simulation side. So in the end, I would like to use this one slide to introduce our 2D experimental pilot lamp project. So it's also a project within this graphene flagship. So here we would like to actually, in these 4 years, we would like to develop a pilot lamp for 2D materials in Europe. So it will be located at AMO and IHP in Germany, and also VTT in Finland, and also IMEC in Belgium. So in the end, we would like to offer multi-project wafer runs to European stakeholders. So in terms of 2D materials based devices, so that actually AMO will run the first MPW run from next year, October. So if you're interested, please have a look to the Graphene Flagship website. So there is part of for the 2D EPL. And so that brings to me to the end of our project. So I would like to acknowledge, of course, all the projects and also our team and also the collaborators. Thank you very much.